Hello everyone and welcome for this online lecture series. I hope everybody is enjoying this design of mechanical system lectures. So we will conduct today one more problem on design of centrifugal pump. Okay, so let's see. We'll start with the problem. A centrifugal pump directly coupled to an electrical motor which is required to discharge 1000 liter per minute of water against the total head of 25 meter. The design should contain following aspect points. Select the suitable motor, electrical motor that is. Then determine the impeller diameter, inlet outlet well angles and the number of vanes. Then determine the diameter of the impeller shaft. Determine the dimension of volute casing and draw the layout of pump. Okay, if such type of problem which ask for lesser marks, normally it is asked for 20 marks, but if it is asked with the marks like 15 or 14 marks, so you have to cut down some design aspects, or you can say design process. So let's see, if it is asked for lower marks, you can use these design process. Also, one more thing is given in this problem, they have directly given the total head. They haven't provided the suction pipe length, then discharge pipe length, the suction head, discharge head. Okay, so nothing is given. So our first process is directly get skipped, where we are calculating the friction losses and all losses. So that is skipped over here because that we are doing to check calculate the manometric head, which could not provide a cavitation in a suction pipe. Okay, so that was we are checking by using that friction losses, velocity losses, etc. Okay, so first of all, just draw a simple layout of a centrifugal pump, uh, which should include the volute casing, curved blades, impeller blades, eye of impeller, then basic impeller, it is already there. So some footwall, strainer, suction pipe, vacuum gauge, delivery pipe, delivery pressure gauge, and the overhead tank. Okay, so these are the main components which you must have to draw in the pump layout. Okay, what is the initial data? Initially, they have provided only two things. That is, first one, discharge, which is in liter per minute, 1000. We can convert it into the meter cube per second. So just divided by 60, you can get, divided by 60 into 1000. So you can get directly uh, liter per minute to meter cube per second. Okay, after conversion, what we get, the value of Q is equal to 0.01667 meter cube per second, and manometric head or total head is given, that is 25 meter. So start with the pipe diameter design. So considering initial velocity is 2.5 meter per second at suction pipe side, and it is increased in a delivery pipe side. So we are considering, assuming the delivery velocity is 3.5 meter per second. To calculate the diameter of the suction pipe, we know the equation. The Q is equal to area into velocity. So here uh, area is pi by 4 d square. Now by using rearranging the equation, what we get, ds is equal to square root of 4q divided by pi vs. So from this equation you can directly calculate the diameter of the suction pipe. So putting all the values, what we get, the suction pipe diameter is 92.13 mm. We can modify this one with the standard value, that is 100 mm. Then delivery pipe. So with the same equation, we can calculate the delivery pipe diameter. Similarly, putting the values related to delivery pipe, that is only velocity, discharge will be same. After that, what we get, the delivery pipe diameter is 77.86. Okay, you can round up this up to the 80 meter per second, sorry, 80 mm. Okay, or you can reduce the diameter so that the output velocity get increased. As the diameter, you can change the diameter, the velocity get changed. I suggest you can reduce the diameter to 75 mm so that your velocity get increased and the output will be getting increased. Just make a correction. Rather than delivery pipe diameter of 80 mm, you can convert it into 75 mm. As the diameter reduces, your velocity get increased, and because of that velocity, your discharge rate will be increased. Next one, the total head or manometric head, which is given, that is 25 meter. Now we can go for calculating the speed of pump. Now, with the help of equation, minimum speed is equal to 10 manometric head raised to 3 by 4 divided by square root of q. So, putting the value of hm and q, what we get? The minimum speed of motor that we can calculate, or you can say minimum speed of pump that we can require is 866.01 rpm. Okay, so that much is speed is required, minimum speed is required of the pump to maintain the proper discharge. Okay, now we are selecting to achieve this, we have to select an electrical motor which rotate at the speed of 1440 rpm, which is a standard prime mover. Next one, selection of centrifugal pump. Now to select a proper centrifugal pump, first of all you have to select a proper type of pump. So based on the specific speed of the pump, you can select the type of pump. So ns is equal to n into square root of q divided by h raised to 3 by 4. So putting the value of n here, we are putting the value of n of the speed of the prime mover, that is a electric motor. Okay, so it is 1440, then value of q and hm, what do you get? Ns is equal to 16.63. Now refer table number 1. So based on the specific speed, the type of centrifugal pump is given. So if it is in between 10 to 30, you can select the low speed radial flow type of centrifugal pump. If it is in between 30 to 50, medium speed radial flow type of centrifugal pump. If it is in between 50 to 80, it is high speed radial flow type of pump. If it is in between 80 to 160, you can use mixed flow type of. And if it is in between 100 to 450, now you have to use axial flow type of centrifugal pump. So here the value of ns is lies in between 10 to 30. So we are using low speed radial flow type of centrifugal pump. So in this way you can select the type of centrifugal pump. Now next, the design of impeller. Now design of impeller contains different steps or different components, different parameters. Let's see one by one. First of all, outlet diameter of impeller. So you can calculate the outlet or diameter of impeller through velocity triangle diagram. Okay, so here you can see the velocity diagram. Okay, so rather than this, you can directly calculate the values with the help of empirical relations. So d2 is equal to ku into u into square root of 2ghm. Okay, so here you can calculate the value of u by using 60 divided by pi n. Okay, Ku is nothing but low speed impeller factor, which is we are considering is 0.95. We know the value of Hn and G. So putting all the values, what we get, the outlet diameter of the impeller D2 is equal to 0.2786, which is nothing but near about 0.28 meter. So round up it into 0.28 meter, that is 280 mm. Okay. Now to calculate the internal inlet diameter of the impeller, we are using empirical relation, that is that internal inlet diameter of the impeller D1 is equal to 0.5 times of D2. So you can directly half the diameter, outlet diameter. So D1 is equal to 140 mm. Now next one, peripheral velocities of impellers. So U1, first one, that is a peripheral velocity, pi d1 and divided by 60. Putting all the values, the initial velocity U1, peripheral velocity U1 is equal to 10.55 meter per second. So outlet velocity, that is peripheral velocity at outlet, U2 is equal to pi d2 and 2 divided by 62. It is 21.11 meter per second. Next one, we have to calculate the flow velocities. So to calculate the flow velocity, Vf1 is equal to psi square root of 2ghm, where psi is nothing but a flow ratio, which is lies based on the type of speed of impeller. If it is low, it is in between, actually it is in between 0.1 to 0.25. If you have a low speed impeller, you can go to start from 0.1. If you have a high speed impeller up to 0.25, you can select the value. We are selecting size equal to 0.15. So putting all the values, what we get, Vf1 is equal to 3.32 meter per second. Now in the case, uh, if you refer the velocity diagram, Vf1 is equal to Vf2. Uh, okay, so whatever the flow velocity is there, if it is same at the start and at the end, then that is a friction velocity, or you can say flow velocity. Uh, if it is the same, then more quantity of water get discharged. If it is increased, then whirling velocity get changed. So to avoid the whirling action, the value of Vf1 should not be changed from start to end. If they change, the whirl velocity get decreased. Okay, to avoid this one, we are keeping Vf1 is equal to Vf2. So Vf2 is equal to 3.32 meter per second. Next one, the inlet vane angle, beta 1, that is if you are using referring the velocity triangle diagram. If we just take a look. Okay, so beta 1, here you can find out the beta 1. V1 is equal to Vr1, U1, Vr1, sorry, this is a Vf1. V1 is equal to Vf1, this is Vr1, this is U1. Okay, initially alpha is equal to 90 degree because it's inlet with the 90 degree. Okay, referring this velocity triangle, beta 1 is equal to tan inverse of Vf1 divided by U1. So tan inverse 3.32 divided by 10.55, what do we get? Beta angle is equal to 17.48 degree. Now outlet vane angle, we are considering a standard one, that is 22.5 degree. Next, width of impeller at the inlet and outlet. So it is denoted by B. For inlet impeller width, B1 is equal to discharge divided by pi D1 Vf1. So putting all the values, what we get? B1 is equal to 11.41 mm. Okay, we are keeping same value, or you can just round up to 11.5. Then B2 is equal to Q divided by pi d2V2. One more thing, if you are increasing the width of impeller, it will impact, or it can increase the weight of the impeller, and which is not a required thing. Okay, so whatever the dimensions you can calculate, you can directly use those dimensions. Okay, so b2 you can calculate by using same equation, that is Q divided by pi d2 vf2. Then what we get, b2 is equal to 5.7 mm. Okay, next one, the number of vanes. For that, z is equal to 13 d1 plus d2 divided by d2 minus d1 sine raised to beta 1 plus beta 2 divided by 2. Okay, so beta 1 17.3, beta 2 22.5, d1 0.28, and d2 d2 0.28, and d1 is 0.14. Okay, putting all the values, z is equal to 13.27. So we need to round up it because there is no half vane or 1/4 vane. So we have to round up. The number of vanes are 14. Okay. Next, about the thickness of the vane. Vane thickness, by considering the manufacturing point of view, because it is made from castings, minimum 6 to 10 mm, in between 6 to 10 mm, we have to keep the diameter thickness of the vane. So here we are considering 7 mm thickness of the vane based on the manufacturing point of view. Next one, now we have to decide the space, or you can say spacing of those veins. We have number of veins are 14, so we have to specify in a particular peripheral diagram. So the inner periphery spacing, that we can calculate S1, which is shown in a diagram. S1 is equal to pi d1 divided by z. So what we get, S1 is equal to 32.41 mm. So for internal periphery, it is passing with a peripheral distance of 32.41. And about the outer periphery spacing, that is S2 is equal to pi d2 divided by z. What we get, S2 is equal to 62.83. Okay, as shown in figure, the outer diameter spacing, periphery spacing is shown by S2, which is shown over here. Okay, so this to this much, that distance we can calculate it, that is 62.83. Next one, we need to calculate the various efficiencies of the centrifugal pump. Now, first efficiency, that is a mechanical efficiency. Mechanical efficiency we are generally considering is a 95%. So we can directly assume that efficiency. Next one, the manometric efficiency, which is calculated by using figure number 3. You can refer the figure. Tan beta 2 is equal to Vf2 divided by U2 minus Vw2. So we don't know the value of whirling velocity at outlet. So that whirling velocity you need to be calculated to calculate the manometric head, manometric efficiency. So by using this equation, you can calculate the Vw2. So initially, putting all the values, what you get, Vw2 is equal to 13.09 meter per second. Okay. Next one, to calculate the manometric efficiency, efficiency is generally calculated the output divided by input. Okay, so the input is nothing but V of Vw1 U1 divided by G, and output is a total discharge, that is a HM. So putting all the values, what we get, the manometric efficiency is 88.75%. Now next one, calculate the volumetric efficiency. So volumetric efficiency Q is equal to 0.05 of actual Q. So the volume get directly reduced. So that's why such things we have considered. Otherwise, you can directly consider it is as a 95%. Okay, but we are considering this equation. The output discharge is reduced by 5%. So capital Q divided by Q plus Q, putting all the values what we get, the volumetric efficiency is 95%, 95.2%. Okay, if you want, you can directly assume it's up to the 95%. Overall efficiency. So the overall efficiency is nothing but the combination of all efficiencies, that is a product of manometric efficiency, volumetric efficiency, and mechanical efficiency. So after multiplying all the factors, what we get, overall efficiency is equal to 78.2%. Next, we have to select the motor. For that, we need to calculate the motor power. So motor power P is equal to rho g h rho g hm into the Q divided by overall efficiency. Putting all the values, what we get, P is equal to 5.2 kilowatt. Referring PSG, the standard electrical motor, which is selected as a three-phase induction motor, having a standard power that is 19 kilowatt with the motor speed for 1440 rpm. You can go to the PAG and you can calculate, you can note down the other specifications also if you want. Next one, the design of impeller shaft. The design of impeller shaft, for that, first of all, we need to the power, which is we have uh, designed. Rather than designed, if you go with the actual power, the diameter of shaft will be huge in size. So we're just using same power which is we calculated. Okay, so that is nothing but 5 kilowatt. 5.227 kilowatt is equal to 2 pi n t divided by 60 into 1000. So putting all the values, what you get, the torque for shaft is 34.66 Newton meter. Now, when we're considering electrical motor for centrifugal pump, we have to consider a minor shock condition. For that, the value of Ka is equal to 1.5. So the design torque Td is equal to K into Ts. So what we get, the design torque is equal to 52 Newton meter. Selecting the material is low plain carbon steel, that is 45C8, having sigma YT value 380 Newton meter square. Sigma UT value is equal to 600 Newton per mm square. So to calculating the tau, we are using these two conditions. Whichever the condition calculating the lower value, we can choosing that value. So tau is equal to 0.75 multiplied by 0.18 times of sigma UT, that is tau is equal to 81 Newton per mm square. For second condition, tau is equal to 0.75 into 0.3 times of sigma UT, which is we get is 85.5 Newton per mm square. The lower value of from both, that is 81 Newton per mm square, which we have considered for further calculation of the shaft. Now design torque is equal to pi by 16 into tau into dsq. So putting all the values, what we get, the diameter of shaft is equal to 14.84 mm, and which can be modified up to 15 mm. If you want, you can increase the diameter more also. So but it should not be too much because it increases the weight of the its own. Then the diameter of the impeller hub. The impeller diameter, you can just using empirical relation, dh is equal to twice of ds. That is the impeller the hub diameter is 30 mm. To calculate the impeller length, you should have to calculate design key first. Based on the key, you can calculate the length of impeller hub. Design of volute casing. In this design, we are just calculating fuse dimension. We are not wholly design the volute casing because it is asked for low marks. Okay. If you want, you can continue the same design which is I taught you in problem number 1. You can refer that those step also. There is no issue. Okay. So first upon all, to calculating the while designing the volute casing, you first of all calculate the volute base circle diameter, that is D3. D3 is equal to 1.07 times of D2. So D3 we calculated is 300 mm. Then calculating the volute base width, that is B3 is equal to 2 times of B1, which is actually depending upon the value of NPSH. If a specific speed of the pump is lesser than 20, you can use relation that the B3 is equal to twice B2. So using that equation, the value of B3 is equal to 11.5 mm. Next one, calculate the minimum thickness of volute casing. As it is, we are considering manufacturing with the help of casting. So gray cast iron, forged gray cast iron, we are considering over here, that is FG 350, having ultimate tensile strength is equal to 350 Newton per mm square. Consider factor of safety is equal to 5. So the design sigma T, tensile stress, is equal to 350 divided by 5 is equal to 70 Newton per mm square. Now water pressure, rho g hm, that is 1000 multiplied by 9.81 multiplied by 25. What do we get? That is 2,45,250 Newton per mm square. So calculating the thickness of minimum thickness of the volute casing, T is equal to D3 into the water pressure divided by 2 sigma T plus 1. Okay, so here we are considering it is like a pressure vessel. So based on that, the whatever the pressure is applied or maximum pressure is applied, it is internal pressure. Okay, so based on this, we are calculating the thickness. So calculated thickness T is equal to 1.52, but as we are manufacturing this component with the help of casting, so in the casting it is impossible to cast the any casting of 2 mm thickness with this such type of a complicated case shape. So minimum thickness is required for manufacturing is 5 to 6 mm. So here the thickness of the casing we are considering is 6 mm. Okay, so that much is the design. If you want, you can add the other components also, but I suggest you first of all check at what how much the marks is assigned to what component so that you can go for design. Okay, so I hope everybody understood the design. If you have any doubt or any query, you can personally call me or you can personally WhatsApp me. um, I'm sharing the link of the design in the chat box so that you can download and start your assignment to solve centrifugal design problems. Okay. One more thing I would like to share with my all students, that for a DMS you must have to continuously in a practice, because it's a design and it's a quite lengthy problems will be appear in examination. So I suggest everybody that weekly you can at least complete one or two designs, so that the process you can very handy with that. And also few important pages with important formulas you can remember very well. If standard data, if you continuously completing the various problems or designs, you will automatically remember the standard data. So while completing the design in a final examination, it will be save your time, as well as it will increase the quality of your design. Okay, so thank you very much. I will share the link in a chat box. Okay, so thank you very much.